So in this video we'll talk about chain complexes. Okay, so previously we defined for any space X, we defined groups C0x, C1x, C2x, etc. With the differentials called D going from ck plus 1 down to ck. We made some effort to prove this fact that D squared is 0. In other words, if you go 2 steps down this tower of groups, then the composite D composed with D, that's just the 0 homomorphism. So now we need to kind of have a name for this sort of general sort of structure and have some algebraic theory about it. So a chain complex is a sequence of abelian groups AN. It's convenient to kind of say that this is defined for all integers n, but it'll often be the case that AN is 0 for all negative n. Okay, but in principle, all these ANs could be non-zero. Together with homomorphisms, dk from ak to ak minus 1. And composite, if you do ak plus 1 and then you do your dk plus 1 to ak, and then dk down to ak minus 1 is 0 for all k. And one might say that more briefly, we just say d squared is 0. Okay, so won't write these subscripts the k unless it's really necessary to do so to clarify a particular point. Okay, so that's what we mean by a chain complex. Okay, so this condition that the image of dk plus 1 is contained in the kernel of dk. Okay, so it links up with the kind of thing we were saying about exactness before. If the composite of 2 maps is 0, then the image of the first map must be contained in the kernel of the next one. So we'll use the following notation. BKA is the image of this dk plus 1. And zka is the kernel of dk from ak and ak minus 1. This is kind of essentially the same notation as we used in the case of the singular chain complex we wrote up there. And hka, okay, so we notice, so we can, in this notation, this relation up here says that bka is contained in zka. And so you've got 2 abelian groups, one inside the other, and so it's meaningful to take quotient group. Zka mod bka. So then if we've got some element z, little z lying in zka, then we'll just write square bracket z for the coset, z plus bka. So that's an element of the quotient group, hka. Okay. So the way this works, remember, the coset is equal to the 0 coset if and only if z lies in the subgroup we're thinking about, and this is by definition the image, so this is if and only if z is d of w for some w. So these are the so-called homology groups, we can summarize what we proved previously. We're saying that these groups C star X, they form a chain complex, and homology of the space X is defined to be the homology of the associated chain complex. Okay, so this was the chain complex associated with space X, and we can take its homology as explained here, and we just defined the homology of the space to be equal to that. So one point to note here, what does it mean to say the homology is 0? That's equivalent to saying, so ZKA or BKA is 0, which is equivalent to saying that ZKA is the same as BKA, which is equivalent to saying that the kernel of this kernel here, ZKA, was defined to be this kernel. That's got to be the same as the image. And that's equivalent to saying the sequence AK plus 1 to AK minus 1 is exact. Okay, so homology is 0 if only if the sequence is exact. So the sort of slogan, homology is a measure of the failure of exactness. The bigger the homology group, the worse the sequence is from further the sequence is from being exact. Okay. Okay, so there's some basic examples of this. So one example, so if we've got any sequence of abelian groups A star, then we can define D to be 0. Okay, that's the most trivial kind of chain complex you might think of. Any sequence of groups, but you just take the differentials to be the 0 homomorphisms. So then what's the homology? That means that ZKA is the kernel of the 0 map. That's going to be the whole of AK, and BKA is the image of the 0 map coming in from AK plus 1. And so the homology, that's going to be the quotient, that's AK mod 0, which is basically the same thing as AK. So, so in this situation, the differentials are 0, then the homology is just equal to the original sequence of groups. So one particular case in which this comes up, suppose we've only got one group in the chain complex. Okay, so you've got your A 0, but then everything else is 0. Okay. Well then, in this case the differentials have to be 0, right? I mean, obviously all these differentials between 0 groups have to be 0, and then this differential here from A0 to 0, because the target is 0, that has to be 0. And then this differential here from 0 to A0, that again, because the source group is 0, that has to be 0 as well. So so the homology is just the same as the original chain complex, so that just means you get your A0 again in dimension 0, and 0 everywhere else. Okay, so in some sense that's a kind of minimal case where you've only got one group. So now let's consider the case where you've got two groups. let's suppose that AK is 0, except possibly when K is 0 or 1. So we've got the kind of situation like this. You've got your A0 here in dimension 0, and then you've got your A1, and then you've got zeros everywhere else. Okay, so here you can have a differential. You've got a D1 from A1 down to A0. It's only this D1 that's the only one that could possibly be non-zero. Everything else, either the domain or the codomain is 0, so every other differential is automatically forced to be 0. And then for K, if K is not 0 or 1, then it's kind of clear that your AK is BKA and ZKA. These groups are all 0, and therefore HKA is also 0. Okay, so nothing happens except in these degree 0 or 1. Well, what's Z naught A? Okay, so that's the kernel of differential going from A0 to 0, so that's just the whole of A naught. B naught A is the image of A1 going by D to A naught. And so your zeroth homology group is A naught mod the image of D1. This is sometimes called the co-kernel of D1. Whereas if we go to A1, Z1A is going to be the kernel of D1, and B1A, that's the image of this map from 0 to A1, which is just 0. So we see that H1A is just it's the kernel of D1. I mean, officially the kernel of D1 mod 0, but taking the quotient by the 0 group doesn't do anything. So you just got the kernel. So here, H0 is the co-kernel of D1, and H1 is the kernel. So we'll have an example about that, which is kind of secretly related to the homology of the circle, topological homology of the circle considered as a space. I won't explain exactly what the relationship is, but there's at least, I'll just tell you there's some relationship. So let's fix some positive integer n, and then we're going to put A0 is going to be a free abelian group generated by some elements called VI. These are this is for I lying in Z mod n. So this is a free abelian group on V0, V1 all the way up to Vn minus 1. So that's isomorphic to Z to the n. And A1 is going to be similarly the free abelian group on some generators that are called EI. So that's also isomorphic to Z to the n. And my D1 from A1 to A0 is given by D1 of EI is going to be VI plus 1 minus VI. I plus 1 so this is interpreted in Z mod n. So D1 of En minus 1. Okay, so you add 1, you get n, but n is 0, so that's V0 minus Vn minus 1. Okay, so I'm going to claim that the homology of this, So I just defined A0 and A1. I want to take all the other groups to be 0. So this is an instance of the previous example. Okay? And so then what's the kth homology? Well, so as before, if k is not 0 or 1, then you just get 0. So what about H1? So H1, well, that's the kernel of this D1 from A1 to A0. So that's the set of things M0, E0 plus up to M n minus 1, E n minus 1, such that D1 of it is 0. And so what's D1 of that? So it's M0, E1 minus E0 plus M1, E2 minus E1 plus, and then you get M n minus 2, oh sorry, these are V's, Mn minus 2, then you get Vn minus 1 minus Vn minus 2, and then plus the last one, you get your Mn minus 1, and then as you said here, you should get kind of Vn, but everything's wrapping around, it's all done mod n, so your Vn will be V0 minus Vn minus 1, so that's got to be equal to 0. Okay, so yeah, let's look at the coefficient of V0 here. Okay, so you've got a Mn minus 1 minus Mn minus 1 V0 and a minus M0 V0. And let's look at the coefficient of V1. Well, here you've got a M0 V1, M0 V1, and then a minus M1 V1. And then the coefficient of V2, you get a plus M1 and a minus M2. And then at the end, if you're looking for the coefficient of Vn minus 1 here, you get a Mn minus 2 minus Mn minus 1 Vn minus 1. Okay. So you've got condition here is, so in order for this to be 0, right, this is a free abelian group, so all these coefficients have to be 0. But what does it mean is coefficients are 0? For this coefficient to be 0, M0 has to be equal to M1, and then M1 has to be equal to M2, and M2 has to be equal to M3, and so on. So yeah, the condition is just that all the MIs should be the same. So if I call this element little h1, that's the sum of all the EIs, then our conclusion is that h upper 1a is just a copy of z generated by this little h1. Okay. So that's our first homology. Now what about the 0th homology? So I'm going to define a map epsilon. That's going to be from my A0, which remember was the free abelian group on these generators VI, to the integers. Okay, so I'm just going to take take the sum of all coefficients here, and so that gives me an integer. Okay, so So in particular, epsilon of mv naught is m, so that means that epsilon is surjective. Yeah, and therefore by the first isomorphism theorem, epsilon induces isomorphism epsilon bar from A0 mod the kernel of epsilon to Z. Okay, now I want to claim that the kernel of epsilon is the same as the image of D1 from A1 to A0. Assuming this, well, A0 mod the kernel of epsilon is just the same as A0 mod the image of D1, which is the same as the zeroth homology group by definition. So we see that the zeroth homology group by this epsilon bar is isomorphic to Z. So in order to prove this claim, so we do epsilon of D1 of EK, that's epsilon, remember D1 of EK is EK plus 1 minus EK, okay, and then epsilon is just giving us the sum of all the coefficients, so you just get 1 minus 1, which is 0, and so that tells us the image of D1 is contained in the kernel of epsilon. On the other hand, suppose we've got some element m naught v naught up to m n minus 1 v n minus 1, and suppose that's in the kernel of epsilon. So that means that m0 plus m1 up to m n minus 1 is 0. Okay, I'll call this x. Okay. So then, x. Well, we can write this as you can write this as mn minus 1 times your vn minus 1 minus vn minus 2. Yeah, and then I'm going to put in an mn minus 1 plus mn minus 2, vn minus 2 minus vn minus 3. Okay, so notice this is working out. I mean, here I've got an mn minus 1, vn minus 1 as I'm supposed to. Looking at the coefficient of vn minus 2, you know, I've got a minus mn minus 1 here, and I put it back in, so I just end up with mn minus 2 times vn minus 2. And then I'm going to do mn minus 1 plus mn minus 2 plus mn minus 3 vn minus 3 minus vn minus 4, etc. And then you get and so this goes all the way down to kind of like to m1, and then you get kind of v1 minus v0, and then if you do it like this, then you've got the right coefficient of vn minus 1, vn minus 2 all the way down to v1. Then you have to put in a mn minus 1 plus mn minus 2 plus all the way up to m0 times v0. Okay, and notice here, here, I mean, this is this is d of en minus 2, d of en minus 3, etc. This is d of E0, whereas this coefficient is equal to 0 by assumption. Right? That was our assumption here. So x is in the image of D. Okay, we've expressed it here as some of these things which are obviously in the image of D. So x is in the image of D as claimed. Okay, so this proves that we've got the right homology for this chain complex. And that will do for this first introduction to chain complexes.